We're going to turn now to a discussion of angular momentum, because it's going to turn out that the energy eigenfunctions for hydrogen are also eigenfunctions of operators that have to do with angular momentum. Let's just recollect what that's going to mean classically first. So if I had a particle with some momentum vector, p, and that particle was some r vector, some position vector from an origin, we could write down its angular momentum as the cross product, L equals R cross P. Now, what we're going to ultimately think about this is we're going to be interested in the electron as our particle, so we'll be thinking about operators and variables having to do with the electron and its momentum, as well as the electron's position relative to the nucleus. So just keep that in mind. Now, this is a cross product, right? And if I have the components of these vectors, so if I have, right, my r vector, classically I can just write that out component-wise as xi hat plus yj hat plus zk hat. And similarly, I can write out the momentum vector component-wise, right, that is p sub x I hat plus p sub y j hat plus p sub z k hat. Well, you might remember from 117, 118 that I can write out the components of the cross product in terms of the components of the vectors. You might have your own favorite mnemonic for remembering how to do that, like the determinant. But I'll just write down one example. So for example, the x component of the angular momentum vector ends up being y p z minus z p y. Now in quantum mechanics, just like we've done before, we can construct an operator associated with the x component of angular momentum by simply taking the classical variables and making them operators. So we have an Lx operator, which we just take as the product of y operator, pz operator, and remember the hat denotes operator here, minus z hat py hat. And just to make this explicit, we can now write down what these operators are. Okay, so the y operator is just y. The pz operator is minus ih bar partial z. And similarly for this other term here, so minus z times minus ih bar partial y. So that's how we can construct an operator Lx hat associated with the x component of angular momentum. We can do likewise and define operators associated with the y component of the angular momentum, as well as the z component of our electron's angular momentum. And we're going to think about this as sort of orbital angular momentum, because it's going to have to do, right, with sort of this, we set this up, as though we had the electron moving relative to the nucleus. Now, classically, in addition to thinking about the individual components, we could also think about the magnitude of this angular momentum vector, and more specifically about the magnitude squared of the vector. So classically, I can think of the magnitude squared of L, and by the Pythagorean theorem, that ends up being, right, Lx squared plus Ly squared plus Lz squared. We can do exactly the same thing in quantum mechanics, because we already know how to construct the operators corresponding to these in QM. So we can have a operator L squared, so L squared hat. This is getting a little clunky notation-wise, so I'm going to follow what most people do at this point, and we'll just write this as L squared operator. And that we get by combining the appropriate quantum operators, Lx squared plus Ly squared plus Lz squared. Now, why did I just go through this? I'm going to get to the punchline as soon as I erase the board. So here's the punchline. The energy eigenfunctions psi and Lm, which as solutions of the time-independent Schrödinger equation are eigenfunctions of the Hamiltonian, or energy operator, turn out also to be eigenfunctions of L squared and Lz. And the eigenvalues associated with those eigenvalues are so L squared, so I'll write without the hat to denote the eigenvalue. That turns out to be dependent on L. It's the product L plus 1 h bar squared. And Lz, the eigenvalue turns out to be m h bar. One comment, this is why, where Knight talked about, instead of L squared, he talked about sort of the orbital angular momentum of the state, and he sort of described this as L being L plus 1 square root times h bar. Nothing sort of inherently wrong with this, although if you were to sort of go through things carefully, the operator you construct and work with really is L squared rather than the square root of it. So there's a few things that I want to point out. So where does this come from? So it turns out that the form of operator L squared turns out to be sort of not obvious, but it turns out to be intimately related to the Laplacian in spherical coordinates. That's sort of where this ends up popping into view for the first time. And the fact that your energy eigenfunctions are also eigenfunctions of things related to angular momentum turns out to occur because the Coulomb potential, the 1 over r potential energy, is spherically symmetric. This is an example of something I think I talked about a bunch of classes ago, namely that there's a deep connection between symmetries in physical laws and fundamental conserved quantities. Turns out that if you have any potential energy that is spherically symmetric, meaning it only depends on r and not on like theta and phi, you will always be able to get your energy eigenfunctions to also be eigenfunctions of these two operators. Now you might be wondering, why z? What's so special about z? There's no particular reason. It's not like z is sort of magically a preferred direction, but it does turn out to be convenient to formulate things this way mathematically, and that's sort of why we sort of pick Lz as the one to work with. It turns out to play nicely, particularly nicely with spherical coordinates, where if you thought about that in a math class, right? Sort of you talk about like the polar angle theta that's like relative to the z-axis. So there's already sort of something that's sort of where when you work in spherical coordinates, you're already sort of picking out something special about the z-axis, and that's sort of loosely speaking why we consider L sub z There's no magic about z direction. Okay. Now, if you go and look at these eigenvalues, it turns out that there's a physical consequence in them about the direction of the electron's angular momentum. Let's take a minute to do a clicker question where you think about that. So the clicker question had you look at this 3-1-1 state, and if we look at what the eigenvalues, right? So for L, right, what we end up for 3-1-1 is that L ends up being root 2 h bar, whereas LZ is h bar. What this sort of says in general is the following. Right, if I look at L, so the square root of this eigenvalue, L is always going to be larger than L sub z. The physical consequence is that if I were to think of L as a vector, the electron's orbital angular momentum, that vector cannot solely lie along the z-axis. I'm now going to go to my computer for a diagram that was in your reading, and I'll talk about that a little bit more from my laptop since I cannot draw that. So here's that diagram from Knight with the angular momentum vectors for our electron. It turns out that this diagram is one we have to take with a big grain of salt. It turns out that there are uncertainty relations associated with the operators for all three components, Lx, Ly, and Lz. If we know that we're in a state with a definite Lz, so if we know we're in an energy eigenfunction where there's a definite value of m, it turns out that there's an uncertainty associated with Lx and Ly. The takeaway is that we cannot know precisely both Lx and Ly, namely we can't be able to precisely locate this vector in a particular direction. We can only say that it's somewhere on this cone. Nonetheless, this diagram is sort of useful for pointing out the idea that the L vector cannot purely lie along the z direction, because if it did, we'd be able to say that both Lx and Ly were 0, which turns out to not be possible. And you can try to interpret this L in terms of the direction that like a spinning particle would be orbiting in, but in quantum mechanics, we really need to be very cautious about saying that there's a particle orbiting, because as we'll see later on, we cannot say that the particle is in an orbit of any kind of fixed radius.